I want to welcome everyone who's here in the room, great crowd, and those online. I have a question. How many people are here joining Saturday Morning Physics for the first time? Wow, that's quite a number of people. You know, there's several people here in the front few rows actually raised their hands. Not everyone, but these are prospective graduate students in physics who are visiting campus for a few days. And we want to welcome them and show them what a great place Michigan is to come and also enjoy today's lecture. So join me in welcoming them. You know, it's a 2-day visit, and we decided to put all of Michigan weather into 2 days. I'm physics professor Tim Chupp. I'm one of the organizers of Saturday Morning Physics, along with Carol Raybuck, Monica Wood, and Christine Idala, who's my faculty co-organizer. And I also wanted to, what is 314? Oh, I wanted to tell you, everybody, that it's March 14th, and you know what that means. 7 days until the Earth reaches the equinox. Okay, and I had lots of questions about pi. It's actually also Donut Day because that's Saturday Morning Physics. So I want to remind everyone who's here and welcome you to Saturday Morning Physics and tell you that we're very grateful for the support of everyone who makes this program possible, and in particular the Dr. Mary Lois Tiffany Endowment, the Hideko Tomozawa Endowment, and the Pulakeshi Diallo Astrophysics Fund, and today the Van Loo Graduate Student Presentation, Van Loo Family Graduate Student Presentation Fund. So that's what we're doing here today, and it's been a great privilege working with our two speakers today. But before I do that, I want to remind you that if you want to learn more about supporting Saturday Morning Physics, please go to saturdaymorningphysics.org, and this coming Wednesday is Giving Blue Day, so pay attention to that. Before introducing our speakers, actually, I want to tell you that at the end of today's presentations, we will have a question and answer period, and we'll have microphones here in the room. And if you'd like to send questions, those online in particular, physics@umich.edu. So, our first speaker today is Justin Berman, who's here. He's a fifth-year PhD candidate in physics, working with Professor Henrietta Elvang on his work in theoretical physics. And he grew up in Manhattan. Justin grew up in Manhattan, and he had a passion for watching sports, including football, which is probably why you came here, because he was an undergraduate at Williams College in Massachusetts, and he joined us here in grad school in 2021. He spent a year at the Kavli Institute for Theoretical Physics, and he will very soon defend his PhD and then move to Princeton as a postdoctoral fellow. Our second speaker is Aaron Chan, actually Dr. Aaron Chan. He defended successfully his PhD dissertation yesterday. 22 hours. How does it feel? Okay. Yeah. Maybe only 20. Okay. And Aaron was born in Mountain View, California, but he grew up in Taiwan. He moved there shortly after he was born. His father was a postdoc at Stanford, and then he went back to Taiwan, where he grew up, and he fell in love with physics and video games. So he came back to California to do his undergraduate work at the University of California at Santa Barbara, and then came to Michigan in 2019 to do his graduate work with Professor Loo Lee, who's here. as well. So he's also, Loo Lee is also our intern chair. I want to tell you also that Aaron is an exceptional teacher. I know this because he was the first graduate student instructor in a new course working with me to get it off the ground on instrumentation and electronics. It's actually a laboratory course. So it's not just being a great instructor, but it's also being exceptionally skilled in the laboratory, which he is, and as you'll see. So he plans to move back to California, closer to his family, and then to look for engaging career opportunities, perhaps in public lecturing. So with that, I'd like to welcome both. Justin will be our first speaker, and he'll tell us about bootstrapping high-energy theories from low-energy clues.
Thank you. Thanks, Tim. Thank you. Thank you all for being here to see me and Aaron tell you a little bit about our research. I'm going to be talking today about work that I do in particle physics using a technique called the S-matrix bootstrap. And so to unpack my title a little bit, I want to start by giving you some sense of what we're going to do today. So the idea is to start with information you get from low-energy experiments, and take this information and do some souped-up version of the scientific method, where you try and take some experiment and make a theory out of it. And what we're going to do is we're going to pull ourselves up by our bootstraps with this experimental information and make some testable predictions beyond what we've actually already measured. But before we do that, before we get to particle physics, I want to give you a tangible sense of how the scientific method works by giving you a little bit of the history of our answer to this question. How do things fall? And so here's my demo, very high-tech demo. I have a golf ball and a coffee filter, and we can drop them. And we can see that the golf ball falls much more quickly than the coffee filter. And you might ask why that is. And when you try and answer that, you should ask, what is the difference between the golf ball and the coffee filter? One difference between these two things is that the golf ball is much heavier than the coffee filter. And so if you think that that's the difference, you'll come to the theory of Aristotle, who said, well, he said some stuff in Greek, and unfortunately I can't read Greek, but to paraphrase, approximately what he said is that how quickly an object falls depends on its weight and what it's falling through. So it can also depend on whether it's falling through air or falling through water. Now, we can test this. We can test this hypothesis. So I have my coffee filter again. I can crush it up. It's the same exact weight. I can drop it against, not the golf ball this time, but this other coffee filter. It was identical to the other one before. And so if this is true, these should fall at the same speed. And in what I hope is a shock to no one, they do not. And indeed, Aristotle was wrong. This was discovered by Galileo, who, according to legend, found this out by dropping things off the Leaning Tower of Pisa. And what he realized is that actually it's not the weight that matters, but just the shape of the thing that matters. But if you look at the dates for when these things were noticed, you'll realize that it took about 2,000 years to see this very simple thing that we realized in about 2 minutes. And so hopefully this is a signal to all of you that we as theoretical physicists should be listening to our experimental colleagues. Now on to particle physics. We should ask, what experiments can we do? What things can we observe in particle physics, since we're now doing particle theory rather than the theory of how things fall? One thing which we can observe, and which I study theoretically, is something called particle scattering. And so my analogy for particle scattering comes from watching this show Tom and Jerry as a child. And the idea of a Tom and Jerry episode is there's this cat, Tom, who's trying to catch the mouse, Jerry. And the idea of an episode is basically Tom runs around trying to catch Jerry. Eventually, they get into a huge fight, and then ultimately, Jerry gets away from Tom. This is sort of similar to a particle experiment, where you take your particles, your Tom and Jerry, you smash them together, they have this big fight, and then at the end of the day, some particles come out, and you can measure the particles at the end. And the idea of doing this experiment is that by measuring things at the end, you can actually learn something about what happened in the middle, what happened during this stuff. Sort of similar to a Tom and Jerry episode, where after the big fight, Tom might have a flat face because Jerry smashed him in the face with a pan, or he might have a shaved head because Jerry's run him over with a lawnmower. Similarly, in an experiment, you can measure these particles that come out and understand what was going on in the middle. And I'm going to show you some actual experimental data, but before I do that, I just want to give you a little bit of context from this relation of this guy, Albert Einstein, E equals mc squared. And the idea of this is that there's an amount of energy associated with things with mass, and that energy is proportional to that mass times the square of the speed of light, where the speed of light is very large number, almost 300 million meters per second. And so, for example, if you want to produce in your scattering experiment a particle with a lot of mass, you're going to need to scatter your particles with even more energy because this speed of light is such a large number. So you're going to have an enormous amount of energy that you need to put into your scattering experiment in order to see particles with lots of mass. And we'll see this play out right now. So here I'm showing data from an experiment called ALICE, which was performed at the Large Hadron Collider, a particle collider in Geneva, which is the most powerful collider we have today. And the idea of this experiment was to have a detector that pinged every time it saw a particle that we call a pion. And so the black dots here are the counts of the number of pions that pinged in the detector. And on the x-axis is the amount of energy that those pions had when they hit the detector. So for example, here we have that there are about 1,000 counts of pions that had about a half of a GeV, or a giga-electron volt, of energy. And so to give you an idea, a sense of what this unit, giga-electron volt, is, this gray dashed line is the amount of energy associated with the mass of the proton. So the proton is a particle that makes up the atoms in your body. And so the amount of energy, the mass of the proton times c squared, gives you some energy that lives at this gray line in this plot. And so now, as we go right, we go to higher energies. We can uncover more of the data. And we see, suddenly, there's a large bump. There's a huge increase in the number of counts of pions that pinged our detector at roughly 0.8 GeV. This, theoretically, corresponds to the fact that we have a particle there. We produce in this stuff a particle called the rho meson. And so in red, you can see the theory prediction that comes from adding up all of the stuff that could affect this process, including the existence of a rho meson, and that red solid curve, that's the theory prediction, matches very well with the experimental data. We can continue on to higher energies and see another bump near the proton energy, but not exactly there. So it corresponds to another new particle that we measure in this experiment called the F0 meson. And we can go even to higher energies and see a third bump corresponding to what's called the F2 meson. And so this is the idea of how we discover particles through experiments. We see bumps in the number of particles that come out, and this is telling you, as a signal, that there was a particle that was being produced in your scattering experiment. And of course, we know that there's a proton as well. It makes up our bodies. But we didn't see a bump corresponding to the proton. So why not? Well, it's just the fact that we're looking at the wrong experiment to see this proton. We would see the bump in a different experiment, just not this one. You might ask, what happens then if I collect all of the bumps across all of the experiments we've ever done as particle physicists, and we put them all together? What would that look like? Well, there's a group called the Particle Data Group that does this, and every few years they make a book, the Particle Data Book. And part of that Particle Data Book is a collection of all of the information we know about all the particles we've ever measured. And so here is the list of particles. In green, I'm giving you the particles we saw in the previous slide. We had the pions, the rho meson, the F0 meson, and the F2 meson. But you can see there are way more particles. But actually, this is just a couple of pages in the Particle Data Book. If you keep flipping through, you'll see there are even more particles. And if you keep going further, more particles than that. And this presents an enormous theoretical challenge for us as theoretical particle physicists, because it's extremely difficult to keep track of so much information all the time. Every time, if you had to do something every time you did a theory calculation, you had to account for every single one of these particles. It would just be completely impossible to do even the most simple calculation. And so what can we do about this? Well, it turns out that there's a beautiful theoretical resolution to this from the theory of quantum chromodynamics, which is related to a fact you may know about the proton, that it's not a fundamental particle. It's actually made up of 3 particles called quarks that are held together by gluons. And so here, Tim graciously brought in his zip-up proton that you can put in little plushies of your quarks and your gluon, hold them together, they all live happily in your proton. And the proposal of quantum chromodynamics, which is a rather radical one, is that in fact this entire zoo of particles that I just showed you is essentially the same thing. It's just quarks that are held together by gluons. And this proposal, which matches experiment quite well, leads to the theory of the standard model, which here I have the quarks, the gluon, and then a bunch of other particles that aren't just quarks held together by gluons. And it's still some number of particles that you have, but far fewer than we had before. And so it's much easier to do theoretical calculations with the standard model than it was with this entire zoo of particles we had. And it's a beautiful theory. I mean, it's amazing. It matches experiment unbelievably well. But even with this theory, it's still difficult to understand exactly what's going on in the zoo. It's difficult to make predictions about the properties of the particles that lived in the zoo that I showed you earlier. The S-matrix bootstrap, which is what I study in my research, one part of the bootstrap can help us learn about what is going on in that zoo. And so to give you an analogy for what's going on in this bootstrap, what we do with the bootstrap, I'm going to tell you how a friend of mine, who isn't a physicist herself, but whose husband is a fellow bootstrapper of mine, explains it to her friends. Basically, what she tells people is that instead of don't think you're a particle physicist. Imagine instead that you're a shepherd, and you've lost your sheep. They've run away. Some of them you might have seen crawling through previous slides of mine, but now they're all collected on a mountain. They're all living on this mountain, and it's difficult to climb the mountain. So you want to know something about where they are. The first thing you might want to do is to build a fence around the bottom of the mountain, so the sheep can't actually escape out into the world. You only have to look on this mountain now. It's still going to be some work to look on the mountain, but at least you don't have to explore all the rest of my slides in order to find them. This is sort of like being a particle theorist. Instead of having sheep lost high up on a mountain, what you have are particles lost at high energies. And you want to find where all of your particles are. As a bootstrapper, the first thing you might want to do is ask, where could my particles even possibly be? What kinds of experiments do I not have to do in order to see particles? This can help our experimental colleagues focus their efforts on things that will actually measure new exciting physics. But you might be wondering what this fence could possibly be. Like, I can't have a physical fence around a bunch of tiny little particles. So the fence in the S-matrix bootstrap is instead fundamental principles about physics. So the first of these principles is called unitarity, and is related to the fact that quantum mechanics is an inherently probabilistic theory. Given an event in quantum mechanics, that event has some number of possible outcomes. Each of those possible outcomes have some probability associated with them. And if I sum, what unitarity is telling us is if I sum over all of the probabilities of all of the possible outcomes, I should ultimately find that the total probability of anything happening at all was 100%. The second principle is the principle of causality, which is just a fancy way of saying that nothing should happen, no event should happen before the effect that caused it. So I shouldn't have some event that occurred before the thing that caused it. Finally, there's locality, which is related to this idea of Einstein's that there should be no what he called spooky action at a distance. So for example, I was in France for a workshop last week where I saw the Eiffel Tower, and I could see the Eiffel Tower because I was local to it. You all, because you are not in Paris, but instead in Ann Arbor, can only see this little model Eiffel Tower that I brought back with me, because you're local to this and not to the Eiffel Tower in Paris. Similarly, particles should only see the effects, or they should only feel the effects of particles that are local to them. And with these principles, we can start putting a fence around the set of possible particles. But it turns out that this fence that we put around the particles is very generic. It's very broad. It doesn't actually tell us all that much about what's going on. So you might ask, what else could we possibly put in to learn about what particles there could be? So one thing we can remember is that we actually measured some of the particles. We have this whole particle data book where we saw particles, and we can put that into the bootstrap as well. We can use the fact that we know something about where the particles are to learn about where other particles might be. In the shepherd analogy, this is like our shepherd who's climbed a little bit of the way up the mountain, but gotten tired halfway up, and now can only find some of his sheep. The sheep have come and they've started talking to him. They've been able to tell him about where the particles higher up the mountain, or the sheep higher up the mountain, are. Similarly, in particle physics, we've measured some of our low-energy particles, our low-energy sheep, and we can ask them where their friends at higher energies are. But to do this rigorously, I'm going to play a theorist's game. And you're going to play this game with me because I'm the speaker today. And the idea of this game is that we had this picture of the proton before, where there are 3 quarks with 3 colors: red, green, and blue. Now, the game we're going to play is, instead of having just these 3 colors, which are a property of quarks, we're going to have more colors. We're going to allow colors like purple and violet and magenta. And we're also not going to think about protons. We're going to think about these pions that we were measuring before, where the pions, again, quarks held together by gluons, but here we have a quark, a blue quark, held together with a anti-blue, yellow antiquark, is the antiparticle of a quark. And the idea is that we have these pions, and we have some universe that has many, many colors, however many colors you want, and I'm going to pretend that I have a friend. I have a friend in this universe that has many, many colors, and I'm going to ask my friend to scatter pions. So my friend is going to smash pions together and then measure pions coming out. The same at this Alice experiment, where they measure the pions coming out. And my friend is going to look for bumps in the plot of measured pions in their universe. And I'm going to ask that anytime we see a bump in that plot in our universe, our friend, the multicolored pion physicist, is going to also measure a bump in the plot of pions in their universe. Now, this example may seem a little bit silly and contrived to you, but hopefully, with the next slide, I'll be able to convince you that the most unrealistic part of this is, in fact, me having a friend. Anyway, you're laughing a little too hard at that. Anyway, so, okay, we have the particles that we measured. We have the pion, we have the rho meson that we saw, we have the F0 meson that we saw, and we have the F2 meson that we saw, and we're going to plot them. We're going to put them on a plot where on the x-axis, I have the mass of those particles times c squared, so the energy associated with the mass of that particle. And on the y-axis, I have a property of the particle called spin. This is something like the particle is sort of spinning around an axis at some rate, and so the pion with spin 0 isn't spinning at all. The rho with spin 1 is spinning with 1 unit of this spin. The F2 is spinning with 2 units. Spin 3 would be 3 units. It would be going faster. 4 units. 5, etc. So the idea is that given that my imaginary friend measured these particles, the same that we saw in the real world, the bootstrap, unitarity, causality, and locality, is able to show that there is required to be a particle in this gray region. This is actually a result of my own research, that this particle must exist in the multicolored world. And you can go and you can look in the particle data book. You flip through the pages, you look for a spin 3 particle that has the right properties that my friend should measure. Indeed, such a particle exists. Now my bound tells us that the S-matrix bootstrap requires that a spin 4 particle lives in this gray region. Again, you look through the particle data book, and you find such a particle. Bootstrap tells you the multicolored particle has to live in this gray region. The particle data book tells you the particle lives here, again, right in the gray region. Spin 6, you've got a region in which you must measure this particle. Particle data book says the particle is there. Spin 7, my multicolored friend has to measure a spin 7 particle in this gray region. And you can flip through the particle data book. You can look through it however long you like. You will never find such a particle in the particle data book. That is one of our high energy, our sheep that's really far up the mountain. We've never seen it before. We don't know where it is. It could be in this gray region. It could not be. But the fact that all the previous particles were living in this gray region required by the S-matrix bootstrap that came in this multicolored world, tells us that it might be interesting to at least consider the idea that such a particle might also exist in the real world within this range. And this is something that we can tell our experimental colleagues as theorists. Maybe you want to go and look in this region. This might be an interesting experiment where you'll see a particle with new and interesting properties. And so this is how we, as bootstrappers and as particle theorists, can help our experimentalist friend learn what experiments might be interesting to do, what to spend their time potentially doing. Okay, so to summarize the talk, first I want to emphasize that there is lots of really, really interesting physics out there that we still just don't understand very well, and that in order to understand this physics better, there is an essential interplay between theory and experiment. Experiment needs to help us inform us about what theory is going on, or what theories we can use, and theory can help inform experiment of what experiments might be practical to do. The S-matrix bootstrap, which we study here, is a way of learning about what is even possible for theories of particle physics. And it leads, in particular, to these bounds on the masses of states in pion scattering, particles in pion scattering. Finally, as a theorist, what's near and dear to my heart is the fact that even studying simplified models, this world with multicolored theories, can teach us new things about the real world that those models are going to be an approximation to. Aren't exactly the same as the real world, but we can still learn things about the real world. And now, what's next? Well, maybe we can learn something about what the size of the bump associated with this unmeasured particle could be. So we can tell our experimentalists how hard will it be to find such a particle, what experiments might be the right experiments to look for such a particle in, things like that. And additionally, we can use the bootstrap to learn about new kinds of particles, not just pions and the scattering of pions, but one example would be the Higgs boson, which is one of the most important elements of the standard model. And ultimately, the goal is to be like our happy shepherd friend who's finally got all of his sheep off the mountain. He's completed his version of the S-matrix bootstrap, the sheep matrix bootstrap, and brought all the sheep home. Thank you.
Well, thank you, Justin, for that rousing presentation. And I'm sure many of us would be happy to be your friend. We're going to have the question and answer period after the second presentation, which is Aaron. So the experimentalist is following the theorist here. And here's Aaron. Get set up real quickly. Aaron Chan, who will tell us about extreme magnetic fields, how and why.
Test? Okay. Hi, everyone. So once again, thank you for coming on a Saturday morning to this talk. And I would like to thank Justin for his invigorating talk on scientific theory. But now we're going to move on to something way more simple, magnets. So today's talk will have three main components. The first component, I'll just talk about how magnets work in general. Then I will talk about the National High Magnetic Field Laboratory and the extremely large magnetic fields we generate at these national laboratories. Then I will discuss the experiments in these large magnetic fields and what we hope to achieve. So magnets, how do they work, right? In general, all magnets generate a magnetic field. So here I have a diagram on the bottom left of a simple bar magnet, and you can see the fields around it. And hopefully, as you all know, the field itself generates a weak magnetic field. And a compass itself is also just a small magnet that tries to align along the magnetic field of the Earth to tell us where north is. So here I have a compass right in front of me, and as we can see, when I leave it alone, it's just pointing towards north. But if I take a bar magnet in my hand, I can move this compass without going near it. Without touching it, sorry. Right? So I can cause it to spin just by making the magnetic field of our compass attempt to align with the magnetic field. Oh, did it not? Yeah. To align with the magnetic field of the bar magnet in my hand. In general, there are two types of magnets. The first type is a permanent magnet, where we have these tiny magnetic domains within the material. And when left alone, in its default state, all these magnetic domains are just pointing in random directions, so that the entire object, such as this iron rod I have in my hand, is not magnetic. So when I put it next to these paper clips, we can see that it doesn't really stick any of the paper clips up. However, if we pass this entire object through an external magnetic field, such as I'm doing here right now, that external magnetic field will cause all the magnetic domains to align and work together. And the thing that makes it a permanent magnet, the permanent part of it, is that even after I remove this external magnetic field, these magnetic domains stay aligned. So now the iron rod in my hand should be magnetic and should be able to stick up some paper clips, although quite weakly. We can, again, scramble these magnetic domains through two ways. The first way is by heating the material up so that the thermal energy causes all the magnetic domains to scramble again. And the second type, which is the type I'm doing in my hand right now, is that we just have a variety of magnetic fields around the rod to try to get the domains to point in different directions. So now the rod should be demagnetized again. The second type of a magnet we can generate is called an electromagnet. So when we pass a current through a wire, it generates a magnetic field, such as the diagram you see here on the left. And when we coil the wires up, we can get all these magnetic fields to point in the same direction, and it will generate a magnetic field through the center of this coil, which we also call a solenoid. And as you can see in the diagrams, the magnetic field generated by an electromagnet is exactly the same as a magnetic field generated by a bar magnet. So here I have a demo demonstrating an interaction between a coil, which will generate I will turn into an electromagnet, and this permanent magnet I have in my hand. Okay, so I can, by using the magnetic field, I can cause the bar magnet to levitate here. Right, I can just make it spin. And then when I turn the current off, the electromagnet will also stop producing a magnetic field, and we should see the bar magnet drop. I'm going to make it stop spinning first. Right, so when I can turn it off, it will just drop. And in general, there are two ways we can influence the strength of the magnetic field generated by an electromagnet. The first is this middle coefficient, n over L. So the n is the number of turns, and L is the length. So this is the turn density. And it should make sense that the more wires we have in the same amount of space, the stronger the magnetic field we can generate. And the second one is simply the current, I. The larger the current we run through the coils, the larger the magnetic field will be generated. So we encounter a lot of magnets in our everyday lives. As I mentioned before, the Earth's magnetic field is just about 50 microtesla, so it's a very, very small value. And even just a simple bar magnet I have in my hand can be 100 times at about 5 millitesla. The rare earth magnets you can buy on Amazon made of like neodymium or other materials is about 1 Tesla. And the electromagnets you see at junkyards is also about 1 Tesla. So that's the one you see on the top right picking up the car. The largest magnetic fields we encounter in everyday lives is usually when you go to the hospital and you get an MRI taken. This is about 3 Tesla. And the largest magnetic fields we generate at our national laboratories is up to 45 Tesla for a steady magnet. So this is where we can get it up to 45 Tesla, and we can hold it at 45 Tesla. And also in pulses, where the magnetic field spikes up to 100 Tesla and back down within a fraction of a second. I've also listed here 1200 Tesla, which is the largest field we have produced in a destructive pulse, where by producing the 1200 Tesla, we just break the magnet. So this is obviously very bad for experiments because we want to be able to run our experiment multiple times. So here I have a demo to demonstrate how an easy way to see to compare the strengths of a magnetic field. So here I have an oscilloscope. I'm waiting for it to turn on. And we should see a green dot. Right, so this green dot is essentially an electron beam. And hopefully the physicists in this room know that when you bring a magnet through close to the motion of an electron, the motion of the electron will bend. So if I take this magnet and I move it towards this beam, we should start to see the beam deflect upwards. And here, I will mark where the beam deflects to the top of the screen. Right, so should be about correct. Let's move to the left here. So now, if I replace this magnet with another one, we can compare if this short magnet is stronger or weaker compared to the long magnet. So now if I move it to the same point, we can see that the deflection is a lot less, and I have to move it a lot closer to get the same deflection to the top of the screen. So now moving on to the National High Magnetic Field Laboratory. There are 3 campuses for what we also call MagLab. The headquarters and the main campus is at Florida State University in Tallahassee, Florida. And this campus hosts all the steady state magnets. So those are the magnets where we can bring it up to some field and just hold it at that field. The second campus is at the Los Alamos National Laboratory in Los Alamos, New Mexico. And this campus hosts the pulse magnets, where the magnetic field goes up very quickly and comes down very quickly. And the third campus is at the University of Florida in Gainesville, Florida. And here they host the high field, low temperature magnets. So in these experiments, they're able to get way closer to absolute zero, but the strength of their magnetic fields is not as large, so I will not discuss them today. So at the Florida State campus, at the Florida State University campus, there are 3 types of steady state magnets. The first type is a superconducting magnet, where we cool the coils of the magnet down to a superconducting state so that there is no resistance in the wires. This means that when we pass a current through the wires, no energy is lost. That causes the operating costs of the superconducting magnet to be significantly cheaper than the next version we will see, but it also means that there is a limit to the strength of the field that we can generate. Because if we generate a magnetic field that is too strong on the coils stop being superconducting, and we just get a worse version of the second magnet, which is a resistive magnet. A resistive magnet, as it implies in the name, has resistance, so it costs a lot of power to run it. When we go to MagLab and use their resistive magnets, we get a power budget, right? We can only run our magnet for so long. But because of that, we also get access to a much higher magnetic field. The coils of the resistive magnets are formed by these copper sheet metal plates called bitter plates, named after physicist Francis Bitter. And essentially, we take these plates and we rotate them while pinning them along the big holes, and we can generate a nice coil, as seen on the right. The third type is a hybrid magnet, where we have the inside be a resistive magnet and the outside be a superconducting magnet. And in this one, we get an in-between cost, because some of the magnetic field is generated by the cheap superconducting magnets, but some of it is generated by the expensive resistive magnets. However, by combining the best of both worlds, we're able to get the highest magnetic fields. Here's a picture of the flagship 45 Tesla magnetic field magnet at Tallahassee. And I guess I didn't provide a good scale, but this magnet is close to 3 stories tall. You can kind of use the ladder. And here on the right on the diagram, I've outlined the superconducting outsert and the resistive insert for this magnet. At Los Alamos, they have the host of pulse magnets, which are powered by capacitor banks, instead of the magnets at Tallahassee, which is essentially hooked up to the city's power grid. So here I have a demo for the capacitor banks and how they can release a lot of power in a short amount of time. So I have a simple soda can here that I'm going to load in this chamber. Then I'm going to charge the capacitor banks here. And then once I get enough charge, I will do a countdown and I will release it. This will be very loud, so I would recommend you plug your ears when I'm about to do that. So I will turn it off, then I will do a countdown, then I will fire it. So we're just waiting here. So what this does is that after the capacitor bank is charged, when I fire it, it will run 2 gigantic currents through 2 coils in this acrylic area, and now generate 2 huge opposing magnetic fields on the can, and then we'll see what happens to it. Giving it a sec. All right. So 3, 2, 1. So as we can see, the large magnetic fields instantly split our aluminum can into 2. And so does anyone want to look at these? Right, so hopefully you saw that it was smoking, right? And if anyone wants to hold this, you'll smell that this thing has a burnt smell. And that also shows to the amount of power you generate when you run a current through a wire, right? So that kind of relates back to the resistive wire, magnets losing a lot of power. So in the pulse magnets at Los Alamos, we see that we get a field up to 100 Tesla, but it's very, very short. We get a huge spike, right? And if we really zoom in on this spike, we see that it goes from 40 Tesla up to 100 Tesla, back down to 40 Tesla in a matter of 20 milliseconds, or 2/100ths of a second. So although these allow us access to much higher fields, it has a very limited scope in time. So that does have a strong condition on the type of experiments that we can run in the pulse magnets. So what do we use these strong magnets for? Right? Solid-state physics. As a solid-state physicist, I study novel and interesting types of materials at quantum regimes. So that is low temperatures and high magnetic fields. And a big part of exploring that is exploring how do electrons move within these materials. And hopefully, we can discover materials that are at the intersectionality of electricity and magnetism. So one thing I study is the concept of magnetoresistance. So a lot of materials have resistance, hopefully, as you know, and the higher the resistance, the harder it is to get a current to go through that material. The phenomena of magnetoresistance is the change in resistance when you apply a magnetic field to it. So here on the top right, that's just delta R over R naught, or the resistance at some field minus the resistance at no field divided by resistance at no field. And on the left, I have a diagram of the magnetoresistance of copper up to 1 Tesla. And you see it has a change of a few percent. In the material I study, titanium zinc, at the same 1 Tesla, we see a change in 2,500%, or 25 times. Right? So some metals are able to exhibit an extremely large magnetoresistance, which we call XMR, versus a lot of conventional metals we know, such as copper, that have low magnetoresistance. Another aspect about XMR is that when we go to higher fields, such as here up to 14 Tesla, the magnetoresistance does not slow down. It just keeps growing. It does not seem to have a peak. And in the highest XMR materials, such as tungsten ditelluride, I've shown on the right, we're going up to 13 million% at 60 Tesla, and it still has no signs of slowing down. It is still getting, the rise is still getting faster and faster. The second thing we investigate in these large magnets, as you can kind of see already in the tungsten ditelluride graph, is the oscillations in the resistance as the magnetic field gets larger. And similarly, we see an oscillation in the magnetization of this material called samarium hexaboride. And both of these oscillations tell us information about how the electron behaves within these materials. Specifically, what they tell us is the band structure. So what the band structure is a curve that tells us the relationship between the momentum of an electron in a material versus the energy of that electron. So at low temperatures, all electrons must follow this curve. They cannot just be wherever they want, right? And here I have a demo explaining why. So here I have a beaker full of marbles, and the bottom of the beaker are the marbles or electrons with low energy, and the top are the electrons with high energy. So here, if I shake the beaker softly, that is as if it is a low temperature state, since the temperature corresponds to the vibrations in our material. And we can see if I shake it slowly, only the electrons at the surface are jiggling, right? The electrons near the bottom of the beaker are locked in place. Whereas if I shake it violently, it will be a high temperature state, and we can see that all the electrons will be accessible. And so you can see some electrons can also escape, which also happens at room temperature. But it turns out when we draw this graph in three-dimensional, in momentum space, right? We're looking at the energy versus momentum, but we know that we can only access the electrons near this 0 value. We get some nice pictures. This is lithium, the lightest metal, and also the metal in like the lithium-ion batteries in your phones. Since it's such a simple metal, we just get a nice sphere. But if we think about copper, which has extra valence electrons, we start to get interesting shapes in our Fermi surface. We get these necks that connect between the different atoms of copper. And now if we move on to something even more complicated, such as the material I study, titanium zinc, we get not just one, but in fact 5 different Fermi surfaces at the energy, and they are all very geometrically complicated. So what we do in these large magnetic fields is try to identify and isolate the effect of these different Fermi surfaces on our electron motion. Solid-state matter has a lot of history in electronics, right? It led to the development of semiconductors and LEDs. It led to superconductors. A more recent, although not so recent, 15 years, I guess, of graphene development over the years. And some future avenues, such as magnetic RAM. Here on the right, I've shown a diagram of a magnetic memory based on total magnetoresistance. So here the arrow on the right can point right or left, and when it's pointing left, aligned with the green arrow, that will have low resistance, and if it's pointed against, towards the right, it will have high resistance. And so the thought is that we can use this as electronic bits, 1 and 0. If we can find a single material which has interesting magnetoresistance based similar to this, then we can develop a device that is significantly smaller and requires less engineering as something as complicated as the magnetic memory I have on the screen. And additionally, last year at MIT, they put out a paper describing a material where when you apply a magnetic field, the amount of current going through that material increases drastically, which is exactly what a transistor does. So development of that will allow us to develop electronics based on not just a charge, but also magnetic field. So the main takeaways from today's talk is that we are able to generate magnetic field using current in coils. We generate huge magnetic fields at the National High Magnetic Field Laboratory in Tallahassee and Los Alamos. And we hope to use these huge magnetic fields to probe interesting solid-state materials in hopes of developing future electronics. Thank you.
Well, thank you, Aaron. And thanks again, Justin. So now we have some time for questions. I did get some questions already that were emailed, and we have a microphone here. Thanks, Monica. So for those in the room who'd like to ask questions or think of questions, please come to the microphone. So we'll give about a minute or so. Usually the room needs to go into a higher energy state for a few minutes. Some particles evaporate out the top. The metaphor is incredible. And then we'll be ready for questions. Incredible means hard to believe. Okay. So questions are not organized for one or the other, so just whom you address the question to, and go ahead, first question.
This is a question for Justin. You've, based on observations of particles with spin 4, 5, 6, you hypothesized the existence of a particle with spin 7. If you identify a particle with spin 7 tomorrow, will you then be looking for a particle with spin 8?
Yeah, exactly.
And is there an end to that, or have you defined a retirement project for you?
No, there is in principle no end to that. So you could in principle have particles of arbitrarily large spin, yeah, these kinds of things actually appear in lots of sort of theories of high energy physics. So string theory, for example, is a theory that has particles, or they're not really particles, they're strings, but you can have objects with spin that's very, very large. And so in order to predict dynamics going on at high energies, you very well may need these particles with large spin, yeah.
There's actually a few questions, so while we're on, on this. One's pretty simple, and the other one I think you need to go over again. So if your graph of energy versus spin, so is the revelation in deciding what the axes should be, or one might look at that and say, well, I could have predicted the next particle by drawing a straight line?
Yeah, so indeed, this is actually that's a very interesting point. The fact that you can draw, it looks like you can draw a straight line is a very old idea that was part of the original S-matrix bootstrap program that happened back in the 1960s. And the principle that these particles on this graph should appear as straight lines is actually what led to the discovery of string theory. And so this is something people have thought of. It turns out that the particles in the real world don't exactly live on straight lines, and so that's why these pions aren't exactly predicted by what you would get out of string theory. And so what I would say the revelation is that there are, in fact, it's not that they live exactly on straight lines, but there are both upper and lower bounds on where the masses of these particles can be.
Okay, and then we had another question, and questions relating the three fundamental restrictions: unitarity, causality, and locality, and specifically how they fit in, but specifically locality, because that implies a distance scale, or may imply a distance scale. So the question really is, how do you localize the distance scale, and what is it?
So what I would say is that locality comes down to our understanding of particle physics as the exchange of what we call force carriers. So things like the gluon in the proton and the photon, which makes up light for electromagnetism. Particles like that can travel over long, or photons in particular can travel over long distances. And so things that happen at long distances, like the things that Aaron was showing, where you have magnets affecting things far away, is because the magnets are exchanging photons, or the pieces of the magnet are exchanging photons with each other. And so there is some locality that is inherent in all of these fundamental particle interactions, but that locality might not be obvious just visually. It comes from the fact that particles get sent out by one object and can reach other objects far away.
Question in the room.
Yeah, with the particles that are in the standard model versus the ones that are in the zoo. Regarding the particles that are in the standard model and the ones that are in the zoo, what distinguishes the two groups?
So the most basic distinction between the two is the particles that are in the zoo correspond, at least as far as we understand, to quarks that are held together by gluons. So they're not individual, they're not fundamental particles on their own, but they're made up, they're composites of other more fundamental things. The other particles in the standard model, as far as we know, are not made up of any more fundamental things, and so all of the particles of the standard model are the things that are genuinely fundamental particles.
So all those hundreds or however many are combinations of?
Exactly. They're just quarks put together. There are these 6 quarks, and you can put those things and the anti-quarks together in different ways, and you can make up all of these sorts of hundreds of different possibilities.
Thank you.
Yeah.
Following that up, one of our online attendees wanted to know if you could explain in a little more detail how the gluons do it, hold things together.
It's a little hard to explain in a satisfying way, I would say. But the idea is basically that the quarks act something like rubber bands. So like you can imagine the quarks are like rubber bands that surround or the gluons are rubber bands that surround the quarks. And so as you pull quarks further and further apart, these rubber bands are going to stretch out a little bit, but try and push these quarks back together. And so the more you pull the quarks away from each other, the stronger the rubber band will try and pull them back. And so the idea is that these rubber bands that come from the quarks, or come from the gluons, are strong enough to keep the quarks contained in some small volume that makes up the proton.
Okay, do you want to talk about color a little more?
Um,
In the sense that is and isn't like electric charge? Leading the witness.
Sure. So it is sort of similar. I mean, it is sort of similar to electric charge in that positively and negatively charged objects that have positive and negative electric charge will be attracted to each other, and positive particles that are objects that have the same charge will be repulsed by each other. And so in quantum chromodynamics, it's not the electromagnetic charge, but the color charge that will determine how particles are collected into groups and not collected into groups. Yeah.
Okay, great, thanks. Question?
Hi. I have a question for each speaker. Maybe first we finish with particle physics. So everything we measured so far are just composites, I guess, of quarks mostly, and other things. Are the particles you predict just other composites? Because, well, I guess it's a highly involved project, but to me it sounds like, you just take a bunch of these little quarks and stick them together. That's not, that's got to be a bit more complicated than just putting together Lego bricks to build bigger.
Yeah, that's correct. So the particles that we predict are exactly more of these composite particles that are made up of quarks and gluons. The difficulty is not in understanding what makes up these particles, but in taking your theory for how these particles are made up and computing what their properties are. Theoretically, it turns out to be an extremely challenging problem for the things that are made up of QCD. QCD corresponds to this thing we call the strong force, and the statement that it is a strong force is exactly why it's difficult for us to compute. The fact that it's strong means that it's hard for us to understand it theoretically. And so that's the difficulty. It's not in understanding exactly what these particles are.
We do have questions for Aaron as well. One sec here, sorry.
I would have one.
Oh, well, okay, that'd be good.
Yes,
Sorry.
I have a very important question about magnets. How big of an magnetic field do you need to make a frog levitate? Because I've seen that in the news. I don't know what field it was. I'm not sure if that was your laboratory, but I don't know.
It was not in our laboratory. I remember seeing that. I don't remember the field, but it want to say around 10 Tesla, maybe, I think. Yeah.
Okay, thank you.
So one question is how the force on the electron arises here, a little more explicitly. So in this demonstration, for example, I'm trying to parse this question a little bit, but in this demonstration, you showed that the electron beam, which is coming from the back to the front of this, and the spot are affected by the magnetic field.
Right, so when you apply a magnetic field perpendicular to the motion of an electron, you get something called a Lorentz force, which, trying to not be too mathy here, essentially the magnetic field bends the path of the electron, so that if we have a huge magnetic field and the electron is traveling through it, the path it will draw will become a circle. But here, our magnetic field is not large enough for that circle to happen, so we just get a slight tilt in the result of the beam. Yeah.
Okay, and it also depends on how fast the electrons are moving.
Right, yeah.
Okay, question here?
This question is for Jason. Jason, can you hear me?
Yes.
I'm not sure he can hear me.
Yeah.
Okay. You talk about quarks, and my first question is, are quarks fundamental particles? And I assume they're not, because you can change one to another, okay? An up to a down and a down to an up. And if that's the case, the pions seem to be part of these quarks, okay? If these pions are part of these quarks, then there must be a limit to your line going up where you run out of parts and you only have enough ingredients in a quark to make so many particles. How do you respond to that?
Yeah, so the first thing that I would say is, indeed, we don't know for sure whether quarks are fundamental particles. We don't know whether there's something that's making them up, but we've never observed any more fundamental constituent of a quark. The pions, rather than the quarks being made up of the pions, it's pions that are actually made up of quarks. So you take a couple of quarks, a quark and an antiquark, and you put them together, and you make a pion. And then the idea of this long list of particles is that you can put these quarks together in different ways. And in particular, what you can do is you can have these quarks, you can put these quarks, connect two of them, and you can make them sort of rotate around each other. And you can make them rotate around each other faster and faster and faster, however fast you like. And those are the things that correspond to new particles in this plot. And there's in principle, no limit on how fast those things can rotate around each other. And so that's why there would be no limit on where the spin, what kinds of spins you can have in your particles.
Question for Aaron. Actually, can you flip back to your spiral magnet? And, oh, that's great, yeah. And kind of explain that picture a little bit more, where the current flows and...
Right, so the current flows up the magnetic field is generated up the axis of the spiral. So the current will flow along the plane of each bitter plate. But since they're contacting each other and rotated and offset, like you see on the right, that causes the overall current to follow the spiral vertically. And that's how you generate the magnetic field.
And are those slits for cooling? Is that?
Yeah, so the big slits is for cooling as well as stability posts, and the small slits is so the sheet metal can flex a little bit, because if it's solid, then it's too brittle, and it will snap under the magnetic field.
I see. Okay. Question?
Yeah, I had a question for Aaron. I wanted to ask, so you were talking about this magnetoresistance idea,
Yep.
and I was wondering, what's the sort of like obstacle course that we're setting up for electrons that causes it that when I apply a magnetic field that it's harder to push them through?
Right, so the first idea is the Lorentz force I just mentioned, right? When we apply a magnetic field, we are deflecting the motion of the electrons slightly. However, the main obstacle to the electrons is that are the impurities and defects within the metal. So we can have stray atoms, or we can have grain boundaries, like different locations of the lattice where the electrons may have difficulty. And the application of magnetic field just essentially causes the electron to take a less conventional path through the metal, which gives them more opportunity to encounter these defects, which will cause them to travel slower, which will manifest as a larger resistance. Yep.
Yeah, and can I just follow up then? So why is it that for copper you don't get a very big effect from this sort of thing, whereas this other metal you do?
I wish I knew, right? That's what I think is on. But we do think that a big part of it is the limitation. Because copper's Fermi surface is roughly spherical, right? We get these necks. right? We get the next, but it's roughly spherical, so the motion of the electrons is not quite limited. It can kind of go in whatever direction it wants, whereas compared to the titanium zinc, I know it doesn't look like it in this cutout, but the motion of electrons on this Fermi surface is actually rather limited. So because it's limited, it cannot dodge the defects as well, let's put it that way. So that's why we get that extreme magnetoresistance in titanium zinc.
Gotcha, thank you.
Here's an interesting question for Justin, which is not not what your talk was about, but it was asking you to take your restrictive principles again, unitarity, causality, and locality, and which ones are important in quantum information and computing, if you know.
Yeah, so the most important one that parades throughout all quantum mechanics is unitarity. Unitarity is extremely important in our understanding of quantum mechanics. Causality is also a very important thing in quantum information. The principle of locality, on the other hand, I mean, we have distinct bits in quantum information, and we act on those bits. And so, in some sense, we sort of by hand violate this locality a little bit when we treat things as discrete objects that live in their own isolated little bubbles. Of course, if we were actually in an actual experiment where we were understanding the complete physics of what was going on, we would restore locality. But when we think about quantum information and quantum computers as isolated qubits, then we can violate things like locality.
That's cool. So correct me if I'm wrong, but in quantum information, the concept of entanglement, namely that there's a quantum state that can be non-local, is that true?
Yeah, yes, in principle, and this is actually where Einstein's quote about no spooky action at a distance comes from, because Einstein didn't really like this idea of entanglement. But there are technical reasons why this non-locality is not such a disaster for these fundamental principles. But I will leave it at that and not try and
Okay, that's great.
give the full explanation. Yeah.
I'm certainly not an expert either. Question here.
Yes, hello. I have a question for Aaron. I saw an article about a football team that is near a large EMF, basically electrical station, the San Francisco 49ers, and I don't know much about it, but I was thinking that it's probably some cope for their injuries, and I was wondering if you've heard about it, and if you've if there's any science behind this EMF being maybe a causation for some of their tendon injuries. And then I was also wondering if these high pulses at a laboratory, if there's any safety precautions that are necessary for people.
Right, so I have heard about that in passing, but I didn't really look into it. So let's begin with the safety features, right? Because magnetic fields can cause issues with your body. The reason why MRI works, magnetic resonance imaging works, is because the water in your body, I think, resonates with the magnetic fields generated by the MR, and that's how they get the image. So there are things in your body that react to magnetic fields. So if you put somebody within a sufficiently strong magnetic field, you can cause injury and possibly even death. However, the magnetic field decreases very quickly as distance. So along all those huge magnets we have at MagLab, and even the ones we have in our own lab here, we have these lines that indicate the magnetic field at a certain distance that tell you if you stay outside of this distance, you'll be perfectly fine. So now onto the 49ers. I don't think it's related because the substation should be fairly far away, right? We're saying that even if we're 2 meters away, it goes as r squared. If we're 2 meters away, it goes a quarter of that, right? So I highly doubt that the injuries to the 49ers is related to the substation. Yeah.
Okay, thank you.
Yep.
Okay, let's conclude with a question for both of you, which is a little bit different. So this is emerging from one of the questions online, which is the limits. So maybe I'll start with Justin. and this was the specific question, is there any limit to how large the spin can be of a particle if you had to
As far as we
more
know,
energy?
as far as we know, there's no limit, and indeed, things like string theory will predict the existence of objects, not particles necessarily, but objects with arbitrarily large spin. You can imagine whatever spin you like, and string theory will predict that there is an object with that amount of spin, for example. So there's a physical theory that has objects with arbitrarily large spin.
And there's no law of physics that would limit that?
No.
Okay, cool. And for Aaron, are there laws of physics that limit how large a magnetic field, even for a very short time, could be produced?
No, theoretically, no. The generation of large magnetic fields really is an engineering problem and not a physics problem. So the 45 Tesla magnet at Tallahassee was the largest steady-state magnet for 20 years, I think. So it first came online in the year 2000. In the year 2019, a team in China finally broke that by going to a record 45.2 Tesla. So it took them 20 years to improve by less than 1%, right? So we can imagine that we could theoretically have a coil so large and have a power generation so well that our magnets, we can get very arbitrarily large magnetic fields, but the coils themselves are under a lot of pressure when you apply such a large magnetic field, and that's the main limit, is that, as I mentioned before, they can't snap and the coils just break in half, essentially, when the magnetic field is too large.
Okay, great. Well, thanks to both of you. I think you've shown us that there probably are no limits to what you two can do in your futures. We wish you good luck, and thank you very much for engaging in Saturday Morning Physics, and we hope your outreach efforts continue throughout your careers. Thanks again.
Thank you.